Welcome back to another Super Magnet Man video. One of the ones we did about 10 years ago was on induced magnetism. And the reason we did it is because we have a lot of customers that were able to use this in a very unique way to help solve a problem in their application. So I wanted to review that again and do it a little bit better and cover a few more things because many other customer applications have occurred since then. So the first thing is, when we're working with customers and they have magnets, they need an application where magnets are going to work. What happens is they can't get the magnet where it needs to be. That's where we've used induced magnetism. As you'll notice in this setup, I have a 2-inch N50 cube magnet. We're going to show you some things like we did before as to how induced magnetism can really help. And then we're going to talk about some applications that we've used it in. As you can see, this large magnet is close to the steel bar. This is just a regular iron bar. If I take these steel balls, you can see the steel balls are not sticking to each other and they do not stick to the bar. But as I get it close to the bar, let's look at a little bit of the scientific information. On top of this magnet is 6,000 Gauss. On the underside of this bar at this point is about 1,000 Gauss. Now, when I put this ball here, it lines up and you see that it is staying. It is staying because this part is closer. All of the flux around the ball is now concentrated on that point, and the bar has its magnetic field where the field is concentrated on that point and makes those two stick together. And it seems kind of strange. Why would this stick to the steel bar more than the magnet would pull it down? And that's because the magnetism where it's being focused to the point makes it stronger. Now, I'm not coming in very close to the magnet or it would snatch it out of my hand. I'm going to line up two balls, coming in from the side with our third ball, our fourth one, and our fifth one. These are 1-inch diameter steel balls. And you can see how they cluster up like this. I can actually jack them up and get them a little closer to the magnet, and they are going to hold to the steel stronger than they are going to pull down to the magnet. Let's take a minute and look and see what would happen with 1.5-inch diameter steel balls. As you can tell over here where the magnet is not, they do not stick. Using the gloves, as I get this close to the steel bar and move to the center, it is holding. One of the things that's making it hold is the induced magnetism. This magnet is inducing a flux in this rail and this ball, and you'll see that it follows it. As we move the magnet back and forth, you can see that the ball is following it. This has some very interesting applications and a lot of our customer needs because of the application we'll talk about in just a minute. Now, we'll add another one up here, another 1.5-inch steel ball, and get it close and let it go. And you can hear the click. It's stuck together, and we have it pulling on this steel bar. So this is one of the things that we like to show with our induced magnetism. Now, at Super Magnet Man, we can't ever stop without getting as big as we can get. We have a 2.5-inch diameter steel ball. We're going to try that next. This 2.5-inch steel ball, I kind of enjoyed having these as an item that we've carried for a little while because my first customer for these was someone testing how well things stand up to hurricanes, and they made a cannon that launched these 2.5-inch diameter steel balls. But we're going to use it a little bit differently. I'm going to put it up here and slide it in to make sure it's holding. And now, we're not going to play with this because this is a very large magnet with a 2.5-inch diameter steel sphere. But what I wanted you to see is that it does, through induced magnetism, hold in this position. We're going to talk just a little bit more about this in just a second. To understand how this is working a little better, what we're going to do is take a look. Our North Pole magnet is going to create a magnetic field that is coming out like this. If you go across the surface, it will spread out like this. As it hits the steel ball, Remember, magnetism likes to travel through steel a lot more than it likes to travel through the air. So instead of traveling through the air, it's going to bend the flux lines and bring them into the steel ball. This steel ball is catching all of the flux in this entire area. So it is a lot of flux that's coming in. But since inside the steel the flux bends to the point, it is going to have an intense point right here. If this is 6,000 Gauss, when we ran some tests on it, we found that the point right here is like 2,500 Gauss right here. But if you did it in free space, if we just measured this exact distance to here, it was only 500 Gauss. So what's happened is the steel ball has gathered all of that flux together, then this whole volume space that it has, and focused it to this point. Now, remember, the steel bar above it is seeing the same flux come from it, but it is also getting an induced flux from the steel ball. Since it's at 2,500 Gauss, it's essentially a magnet, and it is pushing the flux here, so we create an intense field here, and that's why it sticks and holds here better than it's pulling down here. The flux at this point was about 1,500 Gauss, so you can see now why it is wanting to stick up at the top rather than pull down to the magnet. Now granted, if we get the magnet too close, this point will eventually be stronger than this and pull it down. Now let's take a look at how this has been used in some of our customer applications. We've got a couple that I can talk about and share with you. One, I had a customer call and said, we need a magnet in this location, but we can't get a magnet in there. The magnet size we need is not going to fit in this space. And I said, do you have some room outside of that space that we can use? And they said, yes. And I said, well, what are you really doing with it? That's one of the questions I always like to ask is, what are you doing? What do you really want? And they said they had a sensor. This is a little Hall sensor, and this sensor was needed to know when it got in the right area so it could initiate some other electrical action. When we do that, they couldn't get the magnet right here, but they could get a small piece of steel. So what we did is we mounted a piece of steel here and a magnet here so that the flux came out. When it hit the steel, it traveled in the steel to the end, generated a high enough field so that the Hall sensor picked it up, worked like a charm. We had another one with another customer that had an automotive application where they were needing an automatic screwer that was going to take a screw, a machine screw, needed to pick it up with the robot and drill it into the same place. And every now and then the screw would fall off. You would think it would fit, but sometimes it fell off. And they said, how can we keep it so that it never falls off? But we couldn't make a magnet that can take the impact of a hydraulic or a pneumatic screw machine. So what we did was we mounted the magnet up above. This magnetic field induced magnetism in the head of the screwdriver and the screw, so that when they came together, they stuck as if each of them were magnets, finished the screwdriver process, and then went on to the next one and picked up the next one. We have found many ways to use induced magnetism to solve a wide variety of problems. Thanks again for watching, and we'll see you in the next video.